Okay, so let's take a look at 4.7, applications involving exponential functions. So it says over here that if I have an exponential function that looks like this, y equals, now instead of having a k, a d, and a c, let's just say we have an a, b to the power of x. Well, the a value is always your initial amount or your initial value. Your b value will be your growth or decay factor or your common ratio. So I'll write that down, common ratio. And your x deals with your time. So for example, in example number 1, an antique vase was purchased in the year 2000 for $8,000. If the vase appreciates, so it's gaining interest, appreciates in value by 6% per year, what is the estimated value in the year 2040 to the nearest cent? So I'm just going to come up with a table of values first, and I'm going to have my time and the value of the vase. So I have time and I have the value of the vase in terms of time. Now at time 0, I understand that the year is the year 2000, but at time 0 the vase is worth $8,000. Time 0 is the exact same as the year 2000, but in terms of our formula, we're going to plug in what the time is. Your initial time is the year 2000. So initial time, so time 0, the vase is worth $8,000. Now, let's take a look at what the vase would be worth after 1 year. So this is just to kind of figure out what's going on. Now, in order to increase by 6%, it's very important you have to add 6%. It's going to be bigger the next year. You have to add 6% on top of this to get what your vase is worth the next year. So how do you do that? Well, 6%, if I multiply this by 6%, okay, and I use a calculator to do that, I'm going to end up with $480. So $480 is what the vase increases by, appreciates by. It doesn't mean that the vase is now worth $480. No, it's now worth $8,480 because it appreciates by 6%. So you're adding 6% to the previous year. How do I figure out what the vase is worth in year 2? I'd go through the same process. In year 1, the vase is $84.80. And if I multiply that by 6%, so I'll take $84.80 and multiply by 6%, I end up with $508.80. And does that mean that the vase is now worth $508.80? No, it doesn't. It means that it gains $508.80 from the previous year. So now the vase is worth $89.88.80. Okay, so it's very important you understand appreciating by 6%. Now, if I take a look at this and I come up, I already know that this is exponential. It's exponentially growing. If I take a look at this, there's a common ratio. And how do I find out the common ratio? The common ratio is found by taking this number and dividing it by that number. So this divided by that is actually 1.06. And if I also do this divided by that, it's also 1.06. The common ratio is 1.06, or the growth is 1.06. See, you have to multiply by 106%. So if you're adding 6%, if it's appreciating by 6%, you're adding 6% to what it's originally worth. It is now worth 106% of what it was the year before. Okay, so if you come up with a formula for this based on what I have up here, y is your vase, the value of your vase in terms of time. A is your initial value. Your initial value is $8,000. So $8,000 is what goes there. Your base is your common ratio, which is 1.06. It's appreciating by 6%. That's your common ratio, 1.06. And it's to the power of t. and it's t over 1. It's very important you know it's t over 1. I don't write the over 1, but it's t over 1 because it happens per year. Okay? If it happens per year, every year it's changing, then it's over 1. But it's very important that if this changed per decade or per every 10 years, then it would be t over 10, and you'll see why later on. So this is the formula for this situation. Now, if it wants to know what the price of the vase is in the year 2040, you have to understand that you're not going to plug in 2040 there. You're going to plug in 40, because that is how much time has gone by since the initial. So this will be 8,000, 1.06 to the power of 40. Now, when you do this, it's also important to understand that you're not going to do 8,000 times 1.06. You have to first do 1.06 to the power of 40, and then press equals on that, and then multiply it by 8,000, and you should get that the value of the vase at time 40 is $82,285.74. And this is the value of the vase 40 years later, which is in the year 2040. So let's take a look at the next one. The next one deals with doubling time and half-life, and you're going to deal with these things. When you have doubling time, what's happening is that whatever you're dealing with, whether it be bacteria or the vase cost or whatever it is doubling every so often. Okay? Now, I don't personally look at these formulas here. What I do is I follow the same formulas here. So y equals a times b to the power of x. So let's take a look at this. Example 1 says a bacterial culture began with 7,500 bacteria. So that's the beginning. Okay? So the amount of bacteria and time. So maybe I have b for bacteria and time. At time 0, you have 7,500 bacteria. Its growth can be modeled using the formula this, where n is the number of bacteria after t hours. How many bacteria are present after 36 hours? So what they have is actually not b, they have n. It should be n as a function of t, number of bacteria as a function of t, is equal to 7,500 times 2 to the power of t over 36. Now let's explain this formula here. What this formula means is that the initial amount of bacteria is 7,500. 2 is the common ratio. Therefore, it is doubling. Every year it's going to double. So after every increment, it's going to double. So the next increment, this is going to become 15,000. Okay? And then it's going to double again to 30,000. And then it's going to double again to 60,000. Now, does it double every year? No, it does not double every year. It's actually doubling per 36, well, not years, but hours. So this is happening, the doubling is happening per 36 hours. So every 36 hours, this is going to double. See, if I plug in 36, which is what it's asking me here, I'll have n of 36 is equal to 7,500 times 2 to the power of 36 over 36. So n of 36 is going to be equal to 7,500 times 2 to the power of 36 over 36 is 1. So it only doubles once, right? 36 hours later, it only doubles once. And if you do the doubling of 7,500, you're going to get 15,000. Okay? So 15,000 happens after 36 hours. Okay? So this doubling time, it's doubling. This 7,500 is doubling every time. That's the common ratio, the base. But it's doubling every 36 hours. Okay? So it's not going up by ones, it's going up by 36s. Okay? So every 36 hours, this is going to double. So at 72 hours, it's going to be 30,000 and so forth. How many bacteria are present after 72 hours? Well, I just answered that there, but let's just take a look at the doubling time. If I plug in 72, I'm going to end up with 7,500 times 2 to the power of 72 over 36. So n of 72 is going to be equal to 7,500 times 2 to the power of that divided by that is 2. So you're actually doubling twice. So n of 72 is going to be equal to 7,500 times 2 squared is 4, and that, of course, is going to give me, 60,000. So, or sorry, 30,000, my fault. So after 72 hours here, you have 30,000 bacteria. So it's very important you understand if they tell you what the doubling time is. Number one, you know it's doubling, so you know that the common ratio is 2 because you are doubling. But it's not doubling every hour, it's doubling every 36 hours, so it's every 36 hours this is occurring.